Hello friends, welcome to Mu Lessons. So today we will continue with the previous topic, that is the induction motor. Last class we have studied about the starting torque, how to get the maximum starting torque. Now we'll see the effect of change of supply power. Now the torque, in the previous class we have read the starting torque is given as K E2 square R2 by R2 square plus X2 square, and in this case E2 is directly proportional to the voltage as this equation expresses. So we can write T is equals to K2 square V square into R2 by R2 square plus X2 square, and K2 is a constant. So from this equation we rather say it as the starting torque is directly proportional to V square. Therefore you must know this, the starting torque is very sensitive to changes of the value of the supply. A drop of 10% in supply voltage will decrease the starting torque about 20%. You can get this data, means it is so sensitive. This could mean that the motor failing to start if it cannot produce a torque greater than the load torque plus the frictional torque. Now the starting torque of three-phase induction motor, the increase of the rotor impedance and therefore the decrease in the value of the rotor current, but the effect of improved power factors predominates and the starting torque is increased. So in all the types of motors like the squirrel cage and wood motors, we can get starting torque. First of all, we will start with the squirrel cage motor. Since the rotor bars are permanently short circuited, it is not possible to add any external resistance. So squirrel cage motors have a starting torque of 1.5 to 2 times the full load value, and with a starting current of 5 to 9 times the full load current. But in case of wound rotor, the resistance of the rotor circuit of such motors can be increased through the addition of external resistances. So by addition of external resistance we can increase the starting torque according to our requirement. By inserting the proper value of external resistances so that R2 equals to X2, that means the maximum starting torque can be obtained. As the motor accelerates, the external resistance is gradually cut out and until the rotor starts, and the rotor circuit is short circuited itself for running condition. And when it comes up to running conditions, all the resistance are short circuited and it is made to move with a synchronous speed. And on the running condition it behaves similar to that of the squirrel cage motor. Now here are some points about motor under load. These are some theoretical points. I will enclose this PDF along with this video so you can learn it well. And we'll discuss some important parts regarding this, like the torque under running conditions. Now in the previous video you have seen the rotor EMF per phase, rotor reactance per phase, rotor impedance per phase, all the values. So here is a basic data regarding this. The rotor EMF per phase in case of running condition, that means we are considering the slip. E2 is equals to S times of E2. Similarly reactance is S times of original reactance, and hence Z2 R2 and the power factor cos phi. These are the very important values you need to remember whenever dealing with standstill condition or running condition. In case of running condition you will consider the slip. In case of standstill condition S equals to 1, so you need to consider it. Now this is the impedance diagram showing you how it changes, better known as impedance triangle. So in this case the running torque equals to is directly proportional to E2 dash I2 dash cos phi 2 dash. So this dash E2 dash I2 dash you have seen before, all depends upon the slip, and hence the result comes up to be the final result. All multiply all the things and the final result is this: K1 S E2 square into R2 by R2 square plus S X2 square. If the starter supply voltage V is constant, then the starter flux and hence E2 will be constant. So we get the TR, that is the torque at the running condition, equals to K2 S R2 by R2 square plus S X2 square, where K2 is another constant. Now it can be seen that the running torque is directly proportional to the slip from the above equation. If slip increases, the motor speed decreases, the torque will increase, and this running torque is directly proportional to the square of the voltage, that is E2 directly proportional to V. So again we will calculate this torque, where we will put K1 or K2, we can say. There is a constant. The value of this constant given as 3 by 2 pi ns. At starting torque, when s equals to 1, the starting torque is given as 3 by 2 pi ns E2 square into R2 by R2 square plus X2 square. So now, in the previous video we have learnt about how to calculate the maximum torque at standstill condition. Now we will see how to calculate the maximum torque at running condition. The procedure is similar. We have to differentiate it with respect to s in this case and compare it with 0. We'll get R2, that is the resistance per phase, is equals to rotor resistance per phase equals to slip times the rotor reactance. Thus for maximum torque Tm under running conditions, this rotor resistance per phase is equals to slip times the standstill rotor reactance per phase, and hence we get these expressions below, you can see. Now we can sum up these things, like the value of the rotor resistance does not alter the value of the maximum torque, but only the value of the slip at which it occurs. That means it depends upon slip. The maximum torque which varies inversely as the standstill reactance, therefore it should be kept as small as possible. This reactance should be kept as small as possible. The maximum torque varies directly with the square of the applied voltage. To obtain this maximum torque at starting s equal to 1, the rotor resistance must be made equal to rotor reactance at standstill. So these are some important points you need to remember. Now we'll discuss the torque slip characteristics. This torque is given as K2 into S into R2 by R2 square plus S square into X2 square. We have read it before, the motor torque at running condition. Now this is a graph which will show you how torque and slip varies. You can see as the resistance increases, it varies linearly, keeping the maximum torque as constant always. So you need to remember some of these points, like at s equals to 0, that is at slip equals to 0, the torque is equals to 0, so that the torque slip curve starts from the origin. But at normal speed, slip is small, so that Sx2 is negligible as compared to R2, and this torque is directly proportional to slip by R2, or you can say this torque is directly proportional to slip when R2 is constant. Hence the torque slip curve is a straight line from 0 slip to a slip that corresponds to a full load. As slip increases beyond the full load, the torque increases and becomes maximum at s equals to R2 by X2. This maximum torque is an induction motor is called pull-out torque or breakdown torque. Now to have a maximum torque, the term s square x2 square increases very rapidly, so that R2 square may be neglected as compared to s square x2 square, and this torque is given as directly proportional to s by s square into x2 square, which is equals to 1 by s times, and this torque, in this case the torque is inversely proportional to s when reactance is constant. Thus the torque now inversely proportional to slip, hence torque slip curve is a rectangular hyperbola at low resistances, you can see, and at high resistances it follows linearly. But the maximum torque remains the same and is independent of the value of the rotor resistance. Therefore the addition of resistance to the rotor circuit does not change the value of the maximum torque, but it only changes the value of the slip at which the maximum torque occurs. This is the most important thing you need to remember. Now we'll see the full load starting and maximum torques. The expression for full load torque is given as Tf is directly proportional to s r square s slip times R2 by R2 square plus xx2 square. Starting torque is given as R2, as in this case no slip is required at starting condition, so R2 by R2 square plus x2 square. and Tm is directly proportional to maximum, that is the torque, maximum torque always remain constant, is directly proportional to 1 by 2x2. Always note that S corresponds to the full load slip. So we can get these expressions by dividing Tm by Tf. We get the following expression. The Tm by Tf is equals to a square plus s square by 2as, and where a, this a is equals to r2 by x2. So you can easily remember this formula if you remember these terms. But no matter if you have the basic formulas in mind, you don't need to remember all these things, you just need to derive it. Just divide them and you will get the results. No need to mug it up. Now induction motor can always be compared with the transformer. I have explained it before. Because the supply is given to the stator, it develops a rotating magnetic field. The conductors of the rotor cuts those magnetic field and hence induces an EMF. This EMF helps to get a mechanical force or a torque to the rotor and it moves. So you can read this from this PDF. Now another important thing is the speed regulation. The speed regulation decides the efficiency also. It is given as no load current, no load, speed at no load minus speed at full load by full load into 100. If no load speed of the rotor is 800 rpm and its full load speed is 780, then the change is 20 rpm and the percentage speed will be 20 into 100 by 780, that is 2.56%. The speed regulation is 2.56. So this is small, very small numerical. You can do practice many more. At no load, only a small torque is required to overcome the small mechanical losses and hence motor torque is small, that is about 1%. When the motor is fully loaded, the slip increases slightly, that is motor speed decreases slightly. It is because the rotor impedance is low and a small decrease in the speed produces a large rotor current. The increased rotor current produces a high torque to meet the load of the motor, and for this reason the change in speed of the motor from no load to full load is very small. So you need to practice these things a lot before considering them. Now there are several speed control methods of three-phase induction motor. Like the speed is given as n into 1 minus s, that is the slip, into the synchronous speed, and we get the next new speed as 1 minus s into 120 f by p. And this reveals that the speed n of induction motor can be varied by changing the supply frequency, the number of poles on the stator, and the slip s. So this new speed can depend upon the slip, the frequency, and the number of poles. Therefore the practical methods of speed control are either to change the number of stator poles or motor slip, because always we cannot change the frequency. We need a means our commercial supply has a constant frequency, so better to change the slip or the poles. So in case of squirrel cage motor, wound rotor motor, we have several speed control methods. Also you will read about the power factors and equivalent circuit in the higher classes or higher semesters. I am enclosing this PDF. This is a lecture PDF. You can go through it. It's a very nice one. So all the best.